Hello, everyone. I didn't time myself when prepare this presentation, so hopefully it will be not too long. Yeah. So hello again, everyone. I'm Yi-Chun Chen, also go for README. Today I will be presenting our dataset GameTileNet. It is a semantic dataset for low resolution game art. Our goal is to support more flexible and story-aware procedural generation by providing artist-made tiles with rich semantic labels. Okay. So our motivation is procedural generation often lacks of semantic grounding, and also without knowing what the tile represents what. Generated work can feel generic or disconnected from the story. And existing tile sets are usually small and rather fixed, which limited the narrative variety they can support. And although more than diffusion or VLM-based model can generate pixel art, the output typically require very heavy cleanup. Like the alignment or the style often don't match what the game wants. Also affect, meanwhile, artists already created a huge amount of high quality, consistent art, which are game ready. The real issue is that those assets are almost never semantically labeled. So still a lot of efforts required to link the semantic and the visual elements. So we propose GameTileNet trying to fill this gap by connecting visual tiles to semantic meaning and enable more narrative-aware and controllable procedural generation to support PCG system can reasoning about tiles. I already mentioned some of the gaps in the last slide, but again, the GameTile is built to fill all three of these gaps. The first one is even though there are a huge amount of artist-made pixel art online, there is no semantic dataset for pixel tiles, so researchers do not have a shared label resource to build on. And the second one is low-resolution arts are very hard for AI models. At the 16 by 16 or 32 by 32 resolution, most detector or the vision language models fail to identify what in the tiles. And the third gap is there is no existing mapping from narrative concept to visual game assets. So when we try to generate scene from a story, we still need a lot of manual mapping between the story and the visual tiles. So what is the GameTileNet? It's a curated collection of little over 2,000 pixel art objects and tiles. All tiles come from open game art, and they are consistent in style and already game ready. We're focusing on top-down style here. And plus the dataset, we also provide the automatic annotation framework, which I will introduce a little bit in the after slides. And also for helping the use of the dataset to map story elements, we also have exported semantic embeddings for all the assets. And what makes this dataset useful is not just the art, but the semantic labels we attached. We basically focusing on the labels about how to use it and what is it. Each tile has an object name, categories, and super categories, and the gameplay affordance, like whether it is a character or terrain or item or interactable objects. We also include the age adjacency and the connectivity labels so tiles can be placed correctly in the generated scene. Together, these annotations allow us to connect story elements to visual scene. Okay. So to help better understand the annotation task included in this study, this slide shows the overall annotation pipeline. We started by preprocessing the tile set, cutting into individual tiles and segmenting multiple tile objects and computing edge connectivity. Then in the label processing stage, we upscaling the low resolution tiles, run object detection when possible, and classify affordance. Okay, the next slide is going to each task in more detail. Okay. So here is the 4 identified core notation tasks. The first one is adjacency, whether the edge of the 2 tiles actually belong to the same object. And the second is the connectivity, which direction a tile can connect to others. And the object detection, to know what the game object is. And also the object categorization, group the game object with their functional categories, I mean the affordance. And here is the interface we use for notation. And here is how we, the first thing is about the object completeness. Here is how we classify the identified segments based on completeness. Some segments contain 4 objects. I actually put some examples in the table on the slide. Okay, so some segments contain 4 objects. For example, a barrel or a tree that fits and tile inside the image. And other image are partial objects, where the object is cut off or continuous beyond the boundary. And finally, some tiles are textures, like the grace or wood patterns, where the whole tile is just repeating, it's a repeating surface. This schema helps us to understand which tile are directly usable in generation and which one require composition with neighbors. Yeah, and for example, here is the complete object, and what we call it partial is like have half the object and duplicate, like combined together, and also just the texture or the picture, but cannot separately be used. Yeah. Then the affordance labels we used in list 30 was adapted from the gameplay role defined in original VGDL paper. But rather than using the full VGDL ontology, we simplify and recognize it to better match what can realistically be inferred from the 32 by 32 pixel art tiles. We use 5 categories here. The terrain capture, workable, or background surfaces. And environmental objects include static scene elements like trees or walls. Interactive objects represent triggers and mechanisms such as door or switches. Items and collectible cover objects player can pick up or use. And the character or creatures include NPC monster animals. This is designed for 32 by 32 tiles where only certain affordance are more perceivable. And the next part is, this slide shows how our hierarchical semantic labeling schema looks. We borrowed the idea of multi-level semantic organization from dataset like AIDE 20K, which used layered open vocabulary labels to support flexible scene understanding for scene understanding task. For GameTileNet, we adapt that idea into 3 levels. The first level is the detail NAN, the specific asset NANs like the acid dragon or pink flower sort of more detailed NAN. And the group is visually coherent subtypes like dragon or flowers. And the subcategory capture the broader functional or conceptual classes such as creature or plant. This hierarchy helps us to clustering the conceptual similar tiles, support open vocabulary matching, and give multiple levels of abstraction when linking narrative descriptions to assets. So I put some overview of the dataset scale here. We started with around 11,000 row tiles, and after segmentation and grouping, we identify about 1,800 unique objects. We also include objects labeled by original author, including around 2,000, I think. Yeah, we're including detailed author annotations across different object types categories, and we annotate the connectivity and affordance flows. Yeah. The full statistic are actually in the paper, so I will skip it slide for short. Yeah. And here are two diagrams show the distribution of our semantic groups. Here I only show the groups which contains more than 10 examples for clarity. So you can see the categories and that appeared frequently. The top chart show the row counts for each group label, and the bottom chart cluster this group into our supercategory, like the creature, equipment, consumable, environmental object, and so on. The main point here is that the dataset covers a wide range of visual and gameplay relevant categories, not just a few object types. Yeah. So back to this slide again. Let's put the test together into the full annotation pipeline again. Next, I will introduce the detail we use for each task. So for the here is how we automatically decide whether neighboring tiles belong to the same object. We measure the similarity on the shared tile boundary use standard structures similarity score. The threshold was decided by average from human labeled example about adjacency. We take the value around 0.6. If two tiles are similar enough along an edge, we recursively merge them into a larger object. The method works well for cleanly bounded sprites, but there are two failure cases. I put the failure cases here. Yeah. Tiles that share similar texture, but are actually different objects will fail in this method. And objects whose outline happen to be right at the tile boundary, like the chair in here, make the split ambiguous. And the next part is the connectivity. The connectivity tells us which edge of a tile can attach to neighboring tiles, which is important for constructing coherent environment. We divided each tile into 8 direction edge segments. For each edge, we first check whether the pixel strip is non-transparent. If it's empty, then it cannot connect. Then we compare the boundary with the neighbor, also using the structure similarity. If the similarity is above the threshold, we mark it as a valid directional connection. Compared to human labels, we got the F1 score at about 0.63, and an exact match around 43%, which is really good for downstream tasks like assembling terrain or grouping tiles. And the next part is to help the model to interpret tiny pixel tiles. We tried several methods, several upscaling methods, from the simplest bicubic methods to the game-based method to transformer-based or the diffusion-based method. Yeah, each produce different visual qualities, which affect both the detection and the semantic matching. And here is how Len work on this. Okay. So after upscaling for the object detection, we first try the most common way, which is the YOLO models to apply it. But we find that upscaling make YOLO detect more shapes, the more bounding blocks, especially with the ESR game. However, the yellow labels never match our semantic labels because it's trained on the COCO categories that won't overlap with fantasy pixel art tiles. That's why we instead use the bleep captions, which can recognize domain-specific or stylized object with open vocabulary. Those captions align more closely with our group labels, supercategory, and affordance. It might show what a functional item it's close to. Yeah, I have a bar chart here. To understand how well bleep captions reflect our ground truth semantics, we compare the caption with at 3 levels. The first one is direct match to check whether the exact words show up in the caption, or the second level is the synonym, expand the label using WordNet. And the third level is the semantic similarity, use sentence birds embeddings to capture conceptual meanings, such as wizard and maids. That should be the same words. This let us compare not only literal overlap, but also the deeper semantic alignment across upscaling methods. So let's see. Oh, okay. This part evaluates whether we can automatically assign the affordance to each tile. Tiles can belong to multiple rows, so we treat this as a multi-level classification task. We use clip to extract the 512 dimension embeddings for each tile because its learned image features align with natural language concepts, and then train a lightweight multi-layer perceptron. On top of it was the binary cross-entropy loss. Overall, the model performed pretty well, and character and items are easiest to classify, and the terrain and environmental objects are also strong. But the interactive objects are much harder because these tiles are visually subtle and actually have very rare cases for interactive objects. This gives us a good baseline for affordance prediction and show which gameplay rules are naturally harder for visual-based models. And I give an example here about the embedding. This slide shows the concrete example how semantic embedding are stored in GameTileNet. Each tile has its human-defined labels, the detail name group, supercategory, and the affordance tag. And for each of those labels, we compute a 512 dimensional semantic embeddings using O-mini-LM sentence transformer. This embedding let visual system can compare tiles in a continuous semantic space. For example, grouping tiles that are conceptually similar, retrieving assets based on story description, or aligning narrative elements with visual tiles. So this structure is consistent across all of the objects we provide in the dataset, so it's easy to plug into downstream generation or retrieval pipelines. Sorry. I'll speed up a little bit. Okay, this is our fitting exam. Inspired by a parallel work of word to word, we also develop an LLM-driven pipeline that can translate short stories into game scenes. Yeah, some of you maybe already saw us. We use the LLM-generated short story as an open vocabulary testing case and split the narrative into different time frames with predicate triples, so we can check the alignment with the object and visuals. Yeah. And from this study, want to bring some interesting discussion point here. We find that the upscaling helped the visibility, but not the semantics. You'll detect more objects, but because you'll is trained on a real world dataset, it's not fit the fantasy world or any world outside of the real world anyway. Yeah. So standard object detection may not really feasible for understanding pixel art tiles. And in contrast, the blip can describe tiles in an open vocabulary. So when we compare those captions with our labels using direct match synonym or sentence embeddings, we see much better semantic alignment, especially after upscaling. So maybe for Gen AI or PCG, for those words not usually exist in our daily life, maybe it could probably the caption-based or embedding-based method are more promising direction than off-the-shelf object detectors when working on stylized pixel art. Yeah, thank you.